In this video, we're going to focus on how to sketch a curve using first and second derivatives in calculus. So let's go over some basic rules. If a function is increasing, the first derivative is positive. Now, if the curve is moving in a straight line, if it's horizontal, the function is not increasing or decreasing, it's constant. The first derivative is 0. The slope of a horizontal line is always 0. And if the function is decreasing, the first derivative is negative because the slope is negative. Now, anytime the graph has a concave up shape, the second derivative is positive. And if it's concave down, the second derivative is negative. When the second derivative is positive, that means that the first derivative is increasing in value. When the second derivative is negative, that means that the first derivative is decreasing in value. Now let's analyze these two curves. For the top one, on the left side, the function is decreasing. So let's say that at this point, the slope is approximately -1. At the bottom, we have a horizontal tangent line, which means the slope is about 0. And at this point, the function is increasing, so it has a positive slope, let's say +1. So notice that when the second derivative is positive, the first derivative, or the slope, is increasing. From -1 to 0 to 1, those numbers are increasing along the number line. Now let's look at the concave down shape. At this point, the function is increasing, so it has a positive slope, let's say +1. At the local extreme value, or the local maximum, we have a horizontal tangent line, so the slope is 0. And at this point, the function is decreasing, so it has a negative slope. So going from 1 to 0 to -1, we can see that the first derivative is decreasing whenever we have a concave down shape. In calculus, there are 4 shapes that you need to be aware of. Here's the first one. Here's the second. Here's the third. And here is the fourth. So if we look at the first one, the function is increasing. So because the function is increasing, let me write that as f going up, the first derivative is positive. Now if you look at the second graph, the function is decreasing as you move from left to right. So whenever the function is decreasing, the first derivative is negative. Now looking at the next one, here the function is decreasing as well. So the first derivative is still negative. And for the last one, the function is increasing. It's going up as we move from left to right. And so therefore, the first derivative is positive. Now let's talk about the second derivative. Notice that this is a concave down shape. So the two graphs on top, the second derivative is negative because it's concave down. The first derivative is decreasing. Here the slope is 1 and then eventually becomes 0. So going from 1 to 0, f prime is decreasing. And here it goes from 0 to -1. So the slope is decreasing, so it's concave down. Now notice that these two curves form a concave up shape. So therefore, the second derivative is positive, since the first derivative is increasing. If you analyze the slope, here it's about -1, now it's 0. Going from -1 to 0, the slope is increasing. And over here, 0 to about 1, it's increasing as well. Now make sure you know these 4 shapes. What's important is that you know that if the first and second derivative is positive, the graph is increasing at an increasing rate. If they're both negative, it's decreasing at a decreasing rate. If the first derivative is positive and if the second is negative, the function is increasing but at a decreasing rate. And if the first derivative is negative and if the second is positive, the function is decreasing at a decreasing rate. Now let's work on an example. So let's say if we have the function 1/3 x cubed minus x squared minus 3x plus 4. So how can we use the first and second derivative to draw a rough sketch for this particular function? So first, find the first derivative and set it equal to 0. The derivative for x cubed is 3x squared. And the derivative of x squared is 2x. And the derivative of x is simply 1. And the derivative of a constant like 4 is 0. So the first derivative is, the 3's cancel, so it's simply x squared minus 2x minus 3. Now let's set it equal to 0, and let's factor this expression. So what two numbers multiply to -3 but add to the middle term -2? This is going to be -3 and 1. -3 times +1 is -3, but -3 plus +1 is -2. So it's x minus 3 and x plus 1. So the critical numbers in this graph are 3 and -1. Now what you want to do is you want to put those numbers in a number line and create a sign chart. So from left to right, -1 comes first and then it's 3. Now we want to see where the first derivative is positive and when it's negative with respect to these numbers. So let's pick a number that's greater than 3. Let's try 4. If we plug in 4 into the factored form of the first derivative, is it going to be positive or negative? 4 minus 3 is positive, and 4 plus 1 is positive. If you multiply two positive numbers, you're going to get a positive result. Now let's try a number between -1 and 3. So let's plug in 0. 0 minus 3 is negative, and 0 plus 1 is positive. A negative times a positive is a negative result. And if we plug in a number less than -1, like -2, -2 minus 3 is negative, -2 plus 1 is negative. Two negative numbers multiplied to each other will give you a positive result. So now we have our sign chart. The next thing we need to do is find the second derivative. By the way, at -1, do we have a maximum or a minimum? Because the function is increasing and then decreasing, -1 is a max. Now at 3, it's decreasing then increasing, so we have a local minimum at 3. Now our next step is to find the second derivative. So let's differentiate the function x squared minus 2x minus 3 to get the second derivative. The derivative of x squared is 2x, and the derivative of -2x is -2, and the derivative of a constant is simply 0. So let's factor out the GCF, which is 2, and let's set it equal to 0. So we could see that the critical point for the second derivative is 1, which is potentially an inflection point if the concavity changes at that point. So let's put 1 on the number line. So if we plug in a 2 into the second derivative, 2 minus 1 is positive, so the second derivative will be positive. If we plug in 0, a number to the left of 1, 0 minus 1 is negative, so this is the signs for the second derivative. So what we need to do at this point is we need to combine the two number lines into a single number line. So let's go ahead and do that. So on top, I'm going to put the signs for the first derivative, and on the bottom, the signs for the second derivative. So the points of interest are -1, 1, and 3. So to the left of -1, is the first derivative positive or negative? So notice that it's positive. And between -1 and 1, the first derivative is negative, which is between -1 and 3. And between 1 and 3, that's still in this region, the first derivative is negative, but beyond 3, it's positive. So now let's focus on the second derivative. Notice that less than 1, the second derivative is negative. So that includes less than -1 and between -1 and 1. And to the right of +1, the second derivative is positive. So that's between 1 and 3 and beyond 3. So everything to the right of 1, it's positive, and to the left of 1, it's negative. So once you combine the first and second derivative into a single number line, now we can draw a rough sketch of the graph. We don't need this anymore. Now, what type of shape do we have if the first and the second derivatives are both positive? If they're both positive, that means the function is increasing at an increasing rate. So if you remember the shapes that we went over earlier in this video, you'll see that it looks like this. Now what about when the first derivative is negative but the second derivative is positive? And that means that the function is decreasing but it's still concave up. So it looks like this. It's decreasing, but we still have a concave up shape. So it's decreasing at an increasing, or at a decreasing rate, I should say. Now, if they're both negative, that means the function is decreasing at an increasing rate. So it's going to look like this. The first derivative is negative, so it's decreasing, and it has to be concave down, since the second derivative is negative. Now for the last one, the function is increasing, but the second derivative is negative, so it must be concave down, so it's this part of the graph. So it's increasing but at a decreasing rate. So if you connect these shapes together, you're going to get a graph that looks something like this. As you can see, we have a maximum at -1. That's when the first derivative changes from positive to negative. And we have a minimum at 3, where the first derivative changes from negative to positive. The inflection point is right in the middle. That's where it changes concavity from concave down to concave up. So this is the rough sketch of the graph. But now let's put it together on an XY graph. Now the original function was 1 over 3 x cubed minus x squared minus 3x plus 4. So let's find the y-intercept. If we plug in 0 into x, y is going to be 0. So we have the first point, 0, 4. And let's say it's somewhere over here. Now we don't know what the x-intercepts are. And it doesn't look like we can factor this expression, so we're just going to have to get a rough sketch. Now we know at -1 there is a maximum, and at 3 there is a minimum. So the graph should look something like this. So that's a rough sketch of the graph. We don't know how high or how low these 2 points are, but if you want to, you can plug in the x values, get the y values, and see how high and how low they should be. Now let's try another example. Let's graph this function, y is equal to 2x divided by x plus 3. Now for this particular rational function, you really don't need to find the first and second derivatives, but we're going to do it anyway, so you can see how it works. Now what you could do, if you want to use algebra techniques to graph it, you can find a vertical asymptote by setting the denominator to 0. So x can't be negative 3, otherwise the function will be undefined. But at that point, that's where you have the vertical asymptote. But the curve will never touch an x value of 3. Now the horizontal asymptote, notice that the numerator and the degree of the denominator are the same. When you see that, the horizontal asymptote is just going to be 2x over 1x, so it's simply going to be 2. If the function is bottom heavy, meaning that if the degree of the denominator is higher than that of the numerator, the horizontal asymptote will be y is equal to 0. If they're the same, if they have the same degree, simply divide the coefficients of the highest terms, 2x and 1x. Now, if it's top heavy, if the degree of the numerator is higher than that of the denominator, then there is no horizontal asymptotes. Now, if the numerator exceeds the denominator by 1 degree, you may have a slant or an oblique asymptote. But if it's 2 degrees or more, then there's no horizontal or slant asymptotes. So we have a vertical asymptote at negative 3. This should be negative. I don't know why I have positive 3. And there's a horizontal asymptote at positive 2. So on the right side, the graph may look like this, or it may look like this. It's one or the other. Now we can use the first and second derivative test to find out for sure, or you could simply plug in a point and see if it's above or below the horizontal asymptote, which I think it's easier to do it that way. For the left side, it can be like this, or it can be like that. But let's find out using derivatives. To find the first derivative, we'll need to use the quotient rule. So let's say if the top function is f and the bottom function is g, that means f is 2x, f prime is the derivative of 2x, that's 2, g is x plus 3, so g prime is the derivative of that. The derivative of x is 1 and the derivative of 3 is 0, so it's simply 1. Now according to the quotient rule, the derivative of f divided by g is g f prime minus f g prime divided by g squared. So g is 1, f prime, g is not 1, g is x plus 3. F prime is 2 minus f, which is 2x, times g prime, which is 1, divided by g squared, or x plus 3 squared. So that's the first derivative, but let's go ahead and simplify it. So let's distribute the 2 to the x plus 3. So it's going to be 2x plus 6 minus 2x divided by x plus 3 squared. So we can cancel these two. So therefore, the first derivative is equal to 6 divided by x plus 3 squared. Now the critical point is at negative 3. That's where it can change direction. At negative 3, it's undefined. But notice that it's squared. That means that the first derivative is always positive. No matter what number you plug in for x, you will always get a positive result. If you plug in 1, 6 divided by 4 squared is positive. If you plug in negative 8 plus 3 is negative 5, but once you square it, it's positive. So the first derivative is positive everywhere, except at negative 3. It's undefined at that point, so Let's put an open circle at -3. Now that we have the first derivative and we've completed the sign chart, let's find the second derivative. So let's rewrite the first derivative. If we move the x plus 3 from the bottom to the top, the positive 2 exponent will now become -2. So we can use the power rule to find the second derivative. 6 times -2 is -12. And then we need to subtract the exponent by 1. So it's -3. And now let's rewrite it. Let's move it back to the bottom. So now instead of being -3, the exponent is +3. So let's create a new sign chart for the second derivative. The point of interest is still -3. Now if we plug in, let's say, -2, -2 plus 3 is a positive result. But there's a negative on top. A negative number divided by a positive number will give you a negative result. Now what if we plug in a number less than -3? Let's say -4. -4 plus 3 is -1. And when you raise it to the third power, it's still -1. -12 divided by -1 is +12. So the second derivative is positive when x is less than -3. So our next step is to combine the two number lines into a single number line. Let's put the first derivative on top and the second derivative on the bottom. So the only point of interest is -3. The first derivative is always positive, and the second derivative changes from positive to negative across -3. Now I do have to fix something because I have it in the opposite direction. The first derivative is always positive, so that corresponds to those values. So let's put the second derivative on top. Okay, now let's graph it. So we know that when the first and second derivative are both positive, the function is increasing at an increasing rate. It's increasing, so it's going up. There's two ways it can increase. It can increase at an increasing rate or increase at a decreasing rate. But because the second derivative is positive, it has to be concave up, so it's this one. Now, what about when the second derivative is negative and when the first derivative is positive? The second derivative is negative when it's concave down. And the first derivative is positive for the first half of that graph because it's increasing. So it should look something like this. So now we can draw a rough sketch. So at -3, we have a vertical asymptote, and at +2, we have a horizontal asymptote. So to the left of -3, we can see that the function is increasing at an increasing rate. It's going up. So it should look something like this. And to the right of -3, it's increasing at a decreasing rate. So it should look like that. And that's how you can use the first and second derivative to see the shape of the graph. Now let's try a harder example. Let's say that f of x is equal to x times the square root of 4 minus x. What would you do to graph this function? So let's go ahead and find the first derivative. You can rewrite it as 4 minus x raised to the 1/2. Now we need to use the product rule. So let's say f is x and g is 4 minus x raised to the 1/2. So if f is equal to x, f prime is 1, and if g is equal to 4 minus x raised to the 1/2, then g prime is going to be 1/2 times 4 minus x, keep the inside the same, and then subtract the exponent 1/2 by 1. 1/2 minus 1 is the same as 1/2 minus 2/2, which is negative 1/2. And then we need to take the derivative of the inside. The derivative of 4 minus x is negative 1. So don't forget to take the derivative of the nested function. In the last example, when we had x plus 3 as the nested function, the derivative of x plus 3 is 1, so it didn't really change the answer. But for this one, the negative 1 is important. Now, according to the product rule, the derivative of f times g is f prime g plus f g prime. So f prime of x is going to be f prime, which is 1, times g, which is the square root of 4 minus x, plus f, which is x, times g prime, which is this stuff. But I'm going to rewrite it. I'm going to bring this to the bottom so that the negative exponent is positive. So this is the same as negative 1 divided by 2 times 4 minus x raised to the 1/2. But it's positive 1/2 since I moved it from the numerator to the denominator. So now what I'm going to do next is convert this into a radical and multiply negative 1 by x, which is negative x. So this is going to be negative x divided by 2 radical 4 minus x if you rewrite it. So what we need to do is combine these two terms into a single term. So we need to get common denominators. So let's multiply this fraction by 2 radical 4 minus x, top and bottom. Whatever you do to the top, you must always do to the bottom. So we don't need this anymore. So therefore, the first derivative is going to be 2 radical 4 minus x times radical 4 minus x, and on the bottom 2 root 4 minus x, and then minus x over 2 root 4 minus x. Now that we have common denominators, we can combine it into a single fraction. Also, radical 4 minus x times radical 4 minus x is simply 4 minus x. So this is going to be 2 times 4 minus x divided by the common denominator of 2 radical 4 minus x. So now let's distribute the 2. So this is going to be 8 minus 2x minus x divided by this stuff. And now let's combine like terms. So f prime of x is going to be 8 minus 3x divided by 2 radical 4 minus x. Now our next step is to find the critical points, the points of interest. To do that, set the numerator equal to 0 and set the denominator equal to 0 separately. So the point of interest where the denominator is going to be 0, you can see it's going to be 4. When 4 minus x is equal to 0, the entire bottom is equal to 0. So if you add x to both sides, x is 4. And if you add 3x to both sides, you can see that x is 8 over 3. So those are the 2 points of interest. Eight over 3 is about 2.67. So it's less than 4. And this is for the first derivative. So if we plug in a number greater than 4, what's going to happen? Let's say if we plug in 5. Notice that 4 minus 5 is a negative number, and you cannot have a negative number inside a radical. So it's undefined past 4. Now what about between 2.67 and 4? Let's say if we plug in 3. So 4 minus 3 is a positive number, and 8 minus 3 times 3, that's 8 minus 9, that's negative. A negative divided by a positive will give you a negative result. So between 8 over 3 and 4, the function is decreasing. F prime is negative. Now what about less than 2.67? Let's say 0. 8 minus 3 times 0 is a positive number, and 4 minus 0 is positive. A positive number divided by a positive number will give you a positive result. So now we need to find the second derivative. So we need to use the quotient rule. So f is going to be the top function, that's 8 minus 3x. So f prime is going to be the derivative of 8 minus 3x, which is negative 3. G is going to be 2 times 4 minus x raised to the 1/2. So g prime, which is the derivative of that, it's going to be 2 times 1/2. Keep the inside the same. 4 minus x. Subtract 1/2 by 1, that's going to be negative 1/2. Then differentiate the inside or the nested function, which is negative 1. So g prime, once you reduce it, 2 and 1/2 will cancel. So it's going to be negative 1, and if you move this to the bottom and turn it back into a radical, it's negative 1 over 4 minus x. Now the formula for the second derivative is going to be g f prime minus f g prime over g squared. So now we need to make some space. So g, which I got rid of, g was the bottom part of the function, which was 2 times the square root of 4 minus x. F prime is 8, actually it's just negative 3. And then minus f, which is 8 minus 3x, times g prime, which is negative 1 times the square root of 4 minus x, divided by g squared, which is the square of this. 2 squared is 4, and the square of radical 4 minus x is just 4 minus x. The square of a square root is just what's on the inside. So now we need to simplify the expression that we have. So 2 times negative 3 is negative 6. And these two negative signs will cancel. And 1 times 8 minus 3x is simply 8 minus 3x. And let's not forget the radical 4 minus x that's attached to the negative 6. Now I do need to correct a mistake. So I had to edit this video. Now this is what I had a few seconds ago. But what it should be over here is 8 minus 3x. So let's continue from this point. Now what we need to do is we need to clear away this fraction. And so what we're going to do is multiply the top and the bottom by this denominator. And that's radical 4 minus x. So radical 4 minus x times negative 6 root 4 minus x. What is that going to be? The radicals will cancel, and we're going to get what's inside, which is simply 4 minus x. So it's going to be negative 6 times 4 minus x. And then these two will cancel once we distribute this to this term. And that's just going to be plus 8 minus 3x. On the bottom, we can just simply put it together. Now I'm going to rewrite radical 4 minus x as 4 minus x to the 1/2. Because these are like terms, we can add the exponents. 1 plus 1/2 is 3 over 2, or 1.5. So we can just leave it as 3 over 2. Now let's distribute the negative 6. Negative 6 times 4 is negative 24, and negative 6 times negative x is positive 6x. And now let's combine like terms. Negative 24 plus 8 is negative 16, and 6x minus 3x is 3x. So we have 3x minus 16. So this is going to be the second derivative. So now let's set the numerator equal to 0 to get the points of interest, and let's set the denominator equal to 0. So we could see that the denominator is going to be 0 when x is 4. For the numerator, we need to add 16 and divide by 3, so it's going to be at 16 over 3. So let's create a new number line. So the points of interest are 4, and 16 over 3. 16 over 3 is about 5.33. And notice that there's nothing beyond 4. It's undefined past 4. If we plug in 5.3, 4 minus 5.3 is going to be a negative number, and we can't have a negative number inside a square root. Now what about when x is less than 4? Let's try 0. 3 times 0 minus 16 is negative 16, which is a negative number. And 4 minus 0 is positive. A negative divided by a positive number is a negative result. So now let's combine the two number lines into a single number line. Let's put the second derivative on top and the first one on the bottom. So the first derivative is positive when it's less than 8 over 3, and negative between 8 over 3 and 4. Now the second derivative is negative everywhere less than 4. So that includes both of these two regions. Now what type of shape do we have when the first derivative is positive and when the second is negative? The second derivative is negative when it's concave down, and the first derivative is positive for the first half of that graph or that shape, because it's increasing during the first half. So what we have is a shape that looks like this. It's increasing at a decreasing rate. Now what about when both the first and second derivative are negative? The second derivative is negative when it's concave down, and the function is decreasing during the right side of this graph. So we have this shape. Now let's see if we can put this together. So we know that the domain is restricted. X cannot be greater than 4. The function stops at 4. Now remember, the original function is x times the square root of 4 minus x. So the function includes 4. We can plug in 4 into the original function. F of 4 is going to be 4 times square root 4 minus 4. 4 minus 4 is 0. And the square root of 0 is 0, so this is the x-intercept of the graph. Now notice that the other x-intercept is at 0 as well. If you plug in 0, 0 times anything is 0, so the next point is at 0, 0. The maximum occurs at 8 over 3. As you can see, the function increases and then it decreases. So 8 over 3, which is about 2.67, we have a maximum at that region. So this graph looks something like this. It's increasing, and once you reach 8 over 3, it decreases. And we can see that it's always concave down. So that's how you graph it, using the first and second derivative. So that is it for this video. Thanks for watching, and have a good day.